Hello, this is a video about the Qibec 1-bit 1-instruction transistor CPU, as you can see right here. In this video we'll talk about how logic gates within the CPU are implemented using discrete transistors. We'll take a look at how a transistor works in the context of this project, how to make a simple logic gate inverter, what the component values within a logic gate should be, how to make more advanced logic gates like a NOR gate and a NAND gate, and finally we'll show these gates on a breadboard using LEDs and push buttons. So, as a summary, a transistor that is used in this project is an NPN type transistor. Electrical symbol looks like that, well, like this. And in this project we only use it as a switch, which means the switch can be open in case it does not conduct current from top to bottom, or it can be closed, in which case it conducts current from top to bottom. Now, for a transistor, obviously there's no human pushing the switch from the left to close it. Instead there's a current coming in from the left to make another current flow from top to bottom. We'll see how that works in a helper circuit. Circuit like this. We have a positive supply rail VCC. Doesn't matter which voltage that is, just an arbitrary voltage. And let's see what happens at this node, which we will consider the output as a function of this node. And let's only talk about high and low voltages, in other words VCC or ground, nothing in between, because we're using the transistor in this project as a digital switch basically. Okay, first let's connect the input to ground. In this case this circuit behaves like this. VCC like an open, the transistor behaves like an open switch, so no current can flow from top to bottom, and the voltage at this node is VCC because it's being pulled up by this resistor. If you connect the input to the positive supply rail instead, the circuit behaves like this, a closed switch, so now current can flow from top to bottom through the transistor, and in this case the voltage at the node is 0 because the node is connected to ground. So this is a very simple way of using a transistor. The transistor is actually an amplifier, as we will see later, but it's not used as such in this project. Right, now this circuit itself is actually already a logic gate. A very simple one is an inverter. If we label the output Y, and if we label the input A, we can see that the output, actually we did see just now that the output Y is the opposite of the input A. If A is low, Y is high, and vice versa. So this is an inverter or NOT gate, right? This one has one transistor. Later on we will see NOR gate and a NAND gate, which each have 2 transistors. They're not much more difficult than this one, just number of transistors is different. So this is how to connect resistor and transistor within the inverter. Now let's take a look at the component values. You see 2 resistors here, so what's the value of these resistors? Let's first assume, let's first call this resistor R, and let's look at the value of this one. So to do that we should take a closer look at the transistor being used in this project, and it is a BC847, which is general purpose NPN transistor. And for breadboarding I use a very similar BC547, pretty much the same. Like said before, the transistor is an amplifier, and one of the properties is the amplification factor, or the beta, or the gain. and in this case it is around 100. It can be 150, 200, 250, but let's be conservative and let's say 100. What does that mean? It means the transistor would limit the current going through it from top to bottom to be at most 100 times the current coming in at the left side. Okay, so the current through the topmost resistor is at most 100 times the current through the leftmost resistor. But in the case of the Qibec CPU, we actually don't want to make use of this amplification behavior. We would like the we would like the transistor to behave like a switch, so it's either full on or full off, and we don't need this factor 100. So to avoid the amplification behavior, we would like this resistor to determine to limit the current instead of the transistor. And to do that, knowing that the gain is 100 approximately, we can take the other resistor to be at most 50 times, let's say 50 times R, and by doing that you guarantee that the current through the topmost resistor is at most 50 times the current through the leftmost resistor, when we assume that the voltage over both resistors, so this one and that one, is approximately the same, and in this case it is the same. There's a small voltage drop over the base of the transistor, but relative to the supply voltage it's pretty low, so let's ignore that for now. So if we keep this resistor at most 50 times the value of this resistor, we guarantee that the topmost resistor is the one limiting the current instead of the transistor, and the transistor still behaves like a switch. So the limit imposed by the transistor is we never reach that limit. Okay. So we can ignore the amplification behavior for now. Let's look at the other value, the value of the other resistor, what that should be. Yeah, at the start of the project an assumption was made that approximately 1000 transistors would be used as part of the CPU. Now in reality that's more like 650, but that doesn't matter, ballpark figure 1000. And we would like to use, one of the requirements was that the CPU could be used from a USB supply, and USB is 500 milliamps max, right, at 5 volt. Actually, the supply rail of the Qibec CPU is only 3.3 volts at the moment. It's not very important. These voltages are not the same, as you can see. It doesn't make much of a difference. For now, let's be conservative and let's say that we are powering the CPU from a linear power supply. So the voltage difference doesn't matter. The current limit is the only thing that matters now. Now let's say we have 1000 of these transistors in the CPU. This, as we saw, is an inverter. There are some other logic gates that look exactly like this. There's always a pull-up resistor, there's always a transistor, one or two below the pull-up transistor, and a pull-up resistor, so it all looks pretty much the same. So worst case, as you can see, this topmost resistor is much smaller than this leftmost resistor, so the current through the topmost resistor will be dominant. The current through the leftmost resistor will be much smaller, so we can ignore that for now. So let's focus on the topmost resistor. Worst case, if every gate inside the CPU would be configured so that the transistor would conduct, then the current through each of these topmost resistors would be at maximum at most 500 microamps. Right, 500 milliamps, 1000 times 500 microamps. So let's say for convenience 330, let's be conservative. And because this is 3.3 volts, follows that this resistor must be more than 10k. Okay, So that would fit inside the USB power supply. Right, and if we know that this is, well, let's take this number 10K. If we know this one is at least 10K, this is 50 times as much, so that's 500K. Let's say 470K. That's a nice value. Now you see, one transistor is at least a value, and another transistor at the left is at most a value. Now we will look a little bit at input impedance and output impedance of a logic gate. Let's say you have two logic gates, because remember, all logic gates pretty much look the same. They all have a pull-up resistor and a resistor at the input. Let's take two logic gates, leftmost and a rightmost one, connected together so that the output of the leftmost one is connected to the input of the rightmost one. Now the topmost resistor contributes to the output impedance of a logic gate. So in this case, the output impedance of the leftmost logic gate is 10K. It is connected to an input. The leftmost resistor contributes to the input impedance, so input impedance of each input is 470K, let's say that. At least 470K, at most 470K, right? So this is a factor 50, yeah? That's nice. Generally speaking, you would like the input impedance to be at least 10 times the output impedance of the circuit driving it. So in this case we're fine. Except, what would happen if we connect multiple logic gates to one output, so multiple inputs to one output, and even more? Now, if you connect five logic gates in parallel to one single output, you can say that the input impedance of that combined cloud of logic is approximately 100K. So for 5 logic gates connected to one single output, 5 inputs connected to one single output, you would have an output impedance of 1/10 of the input impedance. So that's still okay. So that's called a fan out. Fan out is the number of inputs that can be connected to one output. And in this case it's approximately 5. So if you use no more than 5 inputs connected to one output, you have a factor of 10 between input and output impedance, and that's nice. It's not an exact science. That means you can connect more inputs to a single output, and actually this, from another video, this is an 8-bit latch module from the CPU. And what you see here is one inverter at the top there, the output of which is connected to the input of each of these sub-circuits. So one output is connected to 8 inputs, and this works fine. 10 is also fine. Don't use 20, don't use 50, don't use 100, but 5 or 10 is still fine. So actually what you would like to do in this case is remember that this resistor contributes to the output impedance, this resistor contributes to the input impedance of another logic gate. You would like to minimize this, so let's say this is exactly 10K, and you would like to maximize this input impedance. So let's say it is exactly 470K, right? You want to make the difference as big as possible. Now you can, what the method we just did, we can scale everything with a factor 10. So you can say the topmost resistor is 100K and the input resistor is 4.7 meg ohms. Except you will run into problems because your input will become very sensitive, and not in a good way. It will be sensitive to noise. It will be sensitive if you touch the circuit with your hand. It will you will influence it. Also, the stray capacitances will become a bigger factor because your RC times will become bigger. So that's not good. So let's keep this 470K. That's a nice value. Let's keep this 10K, right? So that's what a logic block, what an inverter looks like, exactly with these values, and this BC 847 or 547 on the breadboard. Now, this is an inverter, as we just saw, with an input A and an output Y. You can extend it very easily by adding another transistor like that, and what you're essentially doing is adding another input B, the same kind of another NPN transistor. This is the same resistor as that one, etc. What you're doing essentially making a NOR gate, NOR, not OR. So it's a NOR gate with an output inverted basically. So you see this output Y is 0 if A is high or B is high, right? Likewise, you can construct a NAND gate, and let's see, by doing it like that, something like that. NAND. That's not AND. So it's an AND gate, basically the functionality of an AND gate with an inverter behind it. So you see the output Y is only 0, is only low if both A and B are high. In all other cases it's high, it's being pulled up by this resistor. Right? So now we have a NOT gate or inverter, NOR gate, and NAND gate. Actually, you don't need all three, but these are very easy to make using this logic family, the Resistor Transistor Logic family. That's this method of combining resistors and transistors to form logic gates. And, basically the whole of the CPU is made out of these three gates. There are AND gates, but AND gates are formed by a NAND gate with a NOT gate behind it. And the CPU is not an example of very efficient use of transistors, right? But one of the project goals was to make software run on hardware, to make hardware that runs software in the simplest way possible. So it doesn't have to be a work of art, it should just work. So that's how it works basically. Now let's look at look at these gates on the board, on the breadboard. Let's use that again, sort of. Yeah, it doesn't matter, I'll hold it like that. What we see is a breadboard, obviously. You have a switch here, an input A, a switch controlling the input A. Input A is indicated by this LED right there. You have an input B, that is a button B, input B, indicated by the LED and controlled by the button there, and three gates. There's an inverter, and you see on the breadboard we don't use SMD components for now, we use the BC547, which is basically the same as the BC847, except, you know, it's a different package and some different specs probably. Inverter only uses one transistor. Actually the value of the transistors, as you can see, is not exactly what we just calculated, but this is so small it doesn't matter. It matters if you make this 1000 times, but not 3 times. NOR gate, as you saw, has 2 transistors and 3 resistors. A NAND gate also has 2 transistors in a slightly different configuration and 3 resistors. Now we have one Y, that was the output. We made, it's not very easy to see, but doesn't matter. There's LED indicating the output. The output is basically this wire. We can stick it at the output of each of these gates to see what happens. Let's first stick it at the output of the inverter. So you see that right away. We use input A now as an inverter input. Input B doesn't do anything. So input A is not activated and output Y is high. You see exactly if we press A, then output Y goes low. So output Y is always the opposite of input A. That's exactly what the inverter should do. For the NOR gate, oops, that's a downside of breadboarding. For the NOR gate, we use both inputs A and B, and you see that the output of the NOR gate is 0 if either A or B, or both is 0, right? So if I press either A, if we activate either A or either B, the output of the NOR gate goes low. That's exactly the function of the NOR gate. You can ignore, it doesn't matter. Okay, let's look at the NAND gate finally. That is, if neither input A and B are activated, so A and B are both low, the output of the NAND gate is high, or 1, indicated by the LED right there. If I press A, nothing happens, the output stays high. If I press B, nothing happens, the output stays high. Only if A and B are pressed, then the output is low, right? So it's basically an AND gate with an inverter behind it. That's the functionality of the NAND gate. So this is very big, but as you can see, right, 2 transistors, 3 resistors, typical NOR or NAND gate. And if you look at this board, I'm not sure from memory what this is, but in one cell of each row, so in one white cell, you see 2 black things. That's the BC847 transistor, and 3 other things. That's a resistor. So these are NAND gates or NOR gates. I'm not really sure which is which. So that's how it works basically. So thank you for watching, and to read more, please visit the Qibec site. That's qibec.org. That's also shown in the video description. And please watch the other videos and let me know what you think. And have a nice day. Goodbye.